of G. There is a one-to-one correspondence between any two right cosets of H in G. Okay, so we will just consider it's very straightforward. Let A, for two right cosets we need two elements. Let A and B be two elements in G. We are now going to define a function from this right coset into this right coset in an extremely straightforward manner. An element in this right coset is of this form HA. Its F image is defined to be just HB. Keep in mind, again I am repeating the same thing. We are in Herstein's topics in algebra. Here functions are written on the right side. Okay, arguments appear on the left. Note that this H is in the subgroup H. So this HB will be in HB, and clearly this is well defined also, because once an element like this is given, once an input is given, for that input this H is uniquely determined. You cannot have two H's, say HA and H prime A, and they are equal but H and H prime are different. That cannot happen because we have the right cancellation law. In fact, since we are writing a proof, we may as well write these things, but in a brief manner. Since the right cancellation law is there in the group G, F is well defined and injective, that is one-to-one. One-to-oneness also is a consequence of the right cancellation law. For that to see, you take any two elements, say H1A and H2A in the domain, and you assume that their F images are equal. You have to prove that the inputs themselves are equal. So by the definition of the function, we then get H1B equal to H2B, but using the right cancellation law, you get H1 equal to H2, and hence H1A is equal to H2A. That proves that F is injective. So instead of writing all those things in detail, we are just simply mentioning that because of the right cancellation law, not only is F well defined, but it's one-to-one or injective also. And clearly F is surjective or onto, because you take any element here, HB, its pre-image is HA. Okay, so that H gives us the pre-image. Also, clearly F is onto. Thus, F is a one-to-one correspondence between HA and HB. Give me a moment. Okay, so we now have an equivalence relation on G, whose equivalence classes have turned out to be nothing but the right cosets of the subgroup. What else? We have proved that there is a one-to-one correspondence between any two such right cosets. Now we are going to make the situation special. So this completes the proof of the lemma. Now assume H is finite. It may happen that we have stumbled upon a finite subgroup of G. H is finite. Then the above lemma but before I write this sentence, I should mention this. Since H itself is also a right coset of H, which is this right coset HE. You take the product of every element of H with E, you will get those elements back. So we get H back. So since this is a right coset of H in G, the above lemma says that all the right cosets of H in G are finite. Why? Because all of them will have a one-to-one correspondence with this particular right coset H. This is finite, so they are also finite. And have order of H elements. So because we are dealing with finite sets, so one-to-one correspondence, having a one-to-one correspondence between two such sets means that the sets have the same number of elements. We can now say number of elements because the sets are finite. And since H has this many elements and all the other cosets also should have an equal number of elements, so all of them have this many elements. Now additionally assume that, okay, we don't have to additionally assume, no, not additionally, this will come as a consequence of our assumption. Let it sit like this. Assume G is a finite group and H is a subgroup of G. Then H is also finite. Then H is also finite since the right cosets of H in G are all non-empty and disjoint the number of distinct right cosets will also be finite. Instead of writing future tense, is also finite. Why? Because you see, okay, by the way, how are we concluding that the right cosets of H in G are non-empty and disjoint? That is because we have identified the right cosets of H in G as congruence classes, and you already know that for a congruence relation, for an equivalence relation, congruence classes I said, no, equivalence classes, we already know that if there is an equivalence relation on a set, then the equivalence classes are first of all non-empty sets, and distinct equivalence classes are disjoint. So that means each equivalence class is on its own in the sense that it has no intersection with another equivalence class that is different from it, and all of them are non-empty. So we can choose one element from each one of them. So if the number of equivalence classes, or in this case the number of right cosets, is infinite, then we can create an infinite subset of G by choosing such elements. This choice of course needs the axiom of choice, but you can understand that we can choose one from each one of them, giving us an infinite subset of G, which is not true because G is finite. So not only is the subgroup H finite, but the number of right cosets of H is also finite. This is being forced by the finiteness of G. Let there be k number of distinct right cosets of H in G. Okay, now you look at the situation. We have the group G and we have a subgroup H here somewhere, and H has right cosets. One of the right cosets is H itself. There are other right cosets also, and they are all disjoint, mutually disjoint. No two distinct right cosets intersect. Okay, so these are all right cosets. Maybe this is HA coming for some element A, this is HB, HC, etc. They are disjoint and their union is G, because we know that if there is an equivalence class, then the equivalence if there is an equivalence relation on a set, then the equivalence classes are disjoint and their union is the entire set. So what do you think the total number of elements in G will be? The total number of elements in G will be the sum of the numbers of elements in the equivalence classes. Because they are disjoint, so we can just take sum, order of some right coset, order of some other right coset, etc. And there will be k such distinct right cosets, so k terms in this sum. But we have proved that all the right cosets of H in G are finite and each one of them has this many elements. So all the terms are equal to order of H. K such terms, so this is equal to K times order of H. We have understood this, now we have to write this systematically. Since the distinct right cosets in G, right cosets of H that is understood are disjoint and their union is G, taking everything into account, we have this equation. We already know how we have got this equation. Not only this piece of information is used, but right cosets having the same number of elements and that number being this one, they are also playing a role. So the final thing is this relation, and this equation gives us a statement which is that famous Lagrange's theorem. We have thus proved. It's slightly weird first going through the proof and then stating the theorem. Actually the theorem has dropped out as a consequence of this discussion, so the proof is in the discussion itself. We have proved the following famous theorem due to Lagrange. I'm not even sure if it's pronounced Lagrange or some other. I know him as Lagrange. The pronunciation may be something else. Joseph Louis Lagrange. Theorem 241. His name is also associated to something called Lagrangian from mechanics. Theorem 241. Let G be a finite group and H be a subgroup of G. Then order of H is a divisor of the order of G. That means in a finite group, the number of elements in any subgroup has to divide the number of elements in the whole group. And this theorem is of central importance in finite group theory because it puts severe restrictions on the subgroups that we can have in a group because of this criterion. And this equation prompts a definition. let G be a group and H be a subgroup of G. We are going to name this number K something. Remember what this K was. K is the set of all distinct right cosets of H in G. The number of distinct right cosets of H in G is called the index of H in G, and we denote this quantity by this symbol, index of H. To emphasize the fact that the background group is G, we write G as a suffix. Sometimes if there is no chance of confusion, we may not write this G also. We may write simply I of H. Note that this definition has been made for a general group and a general subgroup. It is not given that G is finite. If G happens to be finite, then this is the index. If G is finite, then, as we have seen above, index of H in G is K, is that K which is nothing but order of G divided by order of H. G is infinite. If G is infinite, then this quantity may or may not be finite. It may be infinite also. There may be infinite groups, or why maybe, there are infinite groups exist that have, if the group is infinite, it's not necessary that all the subgroups should have infinite index. In an infinite group also you can have subgroup having finite index. That's what we are stating now. Infinite groups exist that have subgroups of finite index. An example can be easily given. You consider the additive group of all integers. In it, you consider the subgroup of all even integers. Okay, this is a subgroup. Now, what are the possible cosets? Let us see. The subgroup itself, of course, is a coset. We have already seen. Now, what about 2j plus 1, which consists of integers that look like this? Note that this coset is nothing but the set of all odd integers, and this is the set of all even integers. Since we know that every integer is either an even integer or an odd integer, so we can write this: j is equal to 2j union 2j plus 1. That is, we have written the set of integers as a union of all even integers and all odd integers. So for this subgroup, there are only two cosets. One is the subgroup itself and the other consists of all the odd integers. That means the index of this subgroup in the group J is 2, number of distinct right cosets. So although the group is infinite, the subgroup is also infinite, but the index is finite. Okay, so such situations may arise. Okay, so let us quickly summarize how we have obtained Lagrange's theorem. We were given a group and a subgroup. First, what we did, using this subgroup, we defined a binary relation between elements of a group. We called it congruence modulo H. Then we noted the fact that the equivalence classes for this relation, we then proved that this is an equivalence relation, and then we noted that the equivalence classes are nothing but the right cosets of H in G. Then we proved that any two right cosets of H in G have a one-to-one correspondence between them. Then we considered a finite group and we got the Lagrange's theorem. It dropped out as a consequence of our attempt to calculate the number of elements in the original group in terms of the number of elements in the subgroup. So from there we have got Lagrange's theorem. However, we need not do all these things. Lagrange's theorem can be understood without using these fancy equivalence relations and all those things. It can be understood just using the group and the subgroup, and we are next going to see that.